Hello everyone, we're back. Welcome to this video where today we're going to be looking at searching and sorting algorithms. Now this is useful for GCSE and for A-level. So let's get started. Now, as far as learning objectives are concerned, you need to know how searching algorithms work. You then need to know about the sorting algorithms, and you need to be able to compare and contrast the said sorting and searching algorithms. Now for one video we're going to get through all you need to know, and the examples we use are going to be in Python. So let's start off by looking at the searching algorithms. Now there's two that you need to know. There's the linear search and then there's the binary search. So with regards to searching through a list of items, an example of searching a sorted list is using a dictionary. So for example, find the word algorithm in a dictionary. Now practically doing this, where would you start? So typically you would start by looking at A, then you're looking AL, ALG, and hopefully after that you should be able to find algorithm with its definition. Another example is if we want to find the word abstraction. Where are we going to start? Well, we're going to move backwards from algorithm to A, then to AB, ABS, ABST, until we find abstraction. So first algorithm we're going to look at, which is an example of the one we've just looked with the dictionary, is the binary search algorithm. Now the binary search involves comparing the midpoint of a dataset and working out if the item in question is higher or lower than this value. So if it's lower than the midpoint, then the second half of the dataset is going to be discarded. Otherwise, the first half is going to be discarded because the item is higher than the midpoint. So in a program, we can define the boundaries of a dataset using pointers, where initially the lower boundary position is 0 and the upper boundary position is the end of the list. So with an algorithm, we calculate this by taking the length of the dataset and subtracting 1. So we have a dataset here. This is our lower boundary. This is our upper boundary. And the midpoint is calculated by adding our two boundaries, and we integer divide by 2. Now the reason we integer divide is because if the dataset is an uneven number, our midpoint would be a decimal. It would be a real in terms of computer science, and we can't have a real as a position because integers are used for counting, and as far as the length of a list is concerned, that is a counting number, so we can only use integers. Now, a good exam question response, as shown here, to explain how a binary search algorithm works. Now, this is where you might want to pause the video and copy out what points are made here, because I think this is really useful, because if you're given the question, how does such and such work, if you can reel off these points and the key factors of it, you will get full marks and we're on the way to a grade 9 or an A star. So, changing boundaries to discard data. So, one of the things that throws a few people is, what is this thing about boundaries? How do you do it? Well, let's say for the dataset we're going to find the number 12. Compared to the midpoint, 12 is greater than the first half of the dataset, so we don't need it. So we move the lower boundary to 1 above the midpoint. So everything before 9 we get rid of. We're not looking at it anymore. And the midpoint is recalculated to be 13. Now the midpoint's 13, we can compare this to 12. But 12 is lower than 13, so we discard all the other data by moving the second half of the list, looking at that, and we move the upper boundary to 1 below the midpoint. So as you can see, the dataset is getting smaller and smaller, but we're doing this by moving the pointers for the lower, upper boundaries and the midpoint. So compared to the midpoint, 12 is greater than 11. So how do we modify this? The midpoint goes to the new midpoint is calculated by adding the upper boundary and the lower boundary, dividing by 2. Now the lower boundary is going to move because we know it's greater than 11, but this is going to move to 1 above the midpoint. So 12 add 12 divided by 2 gives you 12. So now the upper boundary, lower boundary and midpoint, they are all the same. So the worst case scenario for a binary search algorithm, you need to know this, it's log 2 n comparisons, where n is the length of the data set. Now, for those GCSE students who are thinking, hold on, what is log? What is that? Well, log is essentially a one-way algorithm. It takes a number and it converts it in such a way. Now, log 2n, with binary numbers, as we know, we have the heading, so 1, 2, 4, 8, 16, 32, 64, 128, and we place a 1 or a 0 underneath that, and that gets our number. Well, log 2, whatever number you put after that will determine what position this does have in the binary list. So let's say we have a list of 16 items. Well, 16 is the 5th in the binary list, so 1, 2, 4, 8, 16. So 5 comparisons maximum are needed for any number you're finding in a dataset of 12 items. Now, pseudocode, you want to program a binary search algorithm. Luckily enough, I have written one in Python. So what I've done is I've put it in a subroutine, and we can pass in different data to show how a binary search works. So if I run the search, what we'll get, hopefully, should be working numbers. So, for example, enter a number to check if it's a square number. So our data set is a list of square numbers from 1 to 10. And we've used a bit of validation to make sure it is. So, for example, let's say we're checking if 25 is a square number. We know it is. So it'll say item is in the list because it is a square number. On the other hand, we have a data set of 100 items. So we declare that by list, and then we get a for loop to add 100 items. And then we do the comparison of remainder, so that's how we compare. So we enter a number to check if it's an odd or even number. So let's say we enter 34. So this is odd. So this should say that it's not on the list as such. And then we have an even number check. So if we enter 34, it'll say the item is in the list. So it's well worth taking down notes for the binary search algorithm, because that's essentially how it works. On the other hand, we have a linear search algorithm. Now, if a list is unsorted, it can be searched with a linear search. Now, this won't work with binary search, mainly because binary search, it only works on ordered data sets, because the items are in order and you can calculate a midpoint. So, binary search only works on sorted lists. You need to know that. A linear search will compare items one by one until the item you're looking for is found. Now, it's longer than the binary search with regards to time complexity, but it will work for any data set. So that's how we're comparing and contrasting them. So let's say we have a data set of 1,000 unordered items. Instantly, a linear search is the better one because a binary search can't use them. However, you can sort an algorithm, which is what we're going to be moving on to looking at. So again, you might want to program this in your programming language. I myself have programmed this in Python, so if I run this, we have a data set of names. So let's say we're looking for the name Daniel. Now, it's just a odd coincidence, but I like to order my data, so it's just the principle of searching one by one, but this will work even if the data's unsorted. So Daniel, yes, it is in the list, and we use a flag as with binary. So let's say we're looking for the name Harry, it's not in the list. So it goes through one by one using a for loop, compares each item, and then we use a flag. So if we have found it, we're going to set the flag to true, and that will chuck up that yes, we have found it, otherwise it's not in the list. So, as I mentioned, with a dataset of 1,000 items, if they're unsorted, instantly a linear search is better because it'll do the job. But what we can do is we can use algorithms to sort data. And there's two algorithms that we're going to be looking at, the merge sort and the bubble sort. So, sorting by comparison. Now, we've got a lovely little animation down there, and that works with what we're looking at. So, let's say we have a list of items we need to sort. Now we can place the items so that they're ordered. This example shown in the animation is called the bubble sort algorithm. Now I'd like you to pay attention, once this restarts, to the largest item, which is here. Now instantly it moves to the end of the list because it's the largest. This is why the idea of bubble sort comes through. As we go through the list, you will notice that the last item to be sorted, it grows from top to bottom. So the largest item in a dataset will bubble through to the end. It's a bit like if you throw stones into water, the heaviest one will come up last because it's the heaviest, but the lightest will come up first because it's got less weight. So it works by comparing each item in a list to the one next to it. So in this animation, the items being compared one by one, and if an item is bigger, that's what's going to be bubbled through to the end. So if the item that we're looking at, if it's greater, then we're going to swap places. At the end of the first pass, as I said, the largest item will have moved to the end of the list. So how many passes? So let's say we have a data set, so a list of 8 items. 10, 6, 5, 16, 4, 9, 12, 3. So a sorted list looks like that. So try it yourself. Sort the unsorted list using a bubble sort. Now this will take a while, but I will go through it for you and you'll be able to see how a bubble sort works. So as you can see, this is one pass to get the largest item to the end of the list. Now sorry it's a bit messy, but writing with a mouse and a keypad, not so good. But as you can see, items swap when they're larger. Eventually, the largest item at the end of the first pass will have bubbled through to the end of the list. So let's get rid of all of that so that eventually I can show you the sorted list. So it's like that. So sorting the unsorted list using a bubble sort, you can do it if you want, but to save you time, so if you do choose to do this, how many passes and how does this compare to the length? So the answer is that it's n-1 passes for a list of n items in the worst case scenario. So if we remember our animation, going back, as you can see at the end of each pass, the largest item moves to the end of what the dataset is. So it is n-1 passes for exam knowledge. So a bubble sort algorithm looks like this. So program it in your programming language to have a go. If you're Python users, you're very lucky because I have got a copy of the algorithm. But what I want to consider is, why do we use a nested for loop? Well, obviously, the worst case scenario is n-1 passes. So we're going to go through the list, and then we're going to go through each item of the list. But the reason we use -1 here, the reason it's subtract 1 is because, as we've said, the largest item will be at the end of the dataset. Now, dataset I plus 1, this is a very interesting statement. The next item of an array can be existent or non-existent. Now, if we're looking at the last item in a list, the next item does not exist, and you will get an error. So length minus 1 works on the principle and the sort of knowledge that the last item will always be sorted. So let's say we're comparing the second to last item. Obviously, that's going to swap here, so we don't need to look at the next. So it's moving through however many items, and then moving through the swaps. So the other data type, well, the other merge sort essentially is what you need to know as well on top of bubble sort. So the merge sort is where we split the dataset into lengths of 1, and each list is an individual item. But just before I go on to that, I should show you the bubble sort algorithm in Python. So in Python, again, I have used a function, so we can pass data into it. So for the length of the dataset, -1, we do that. And what we can get is, for example, the first dataset. We have 619, that sorts it there. Square numbers, they're sorted. And then we have a list of random numbers, they're sorted. So, as you can see, the bubble sort it's good, but it takes a long time. I mean, if you go through each item one by one, it just doesn't work. Now, the other algorithm is the merge sort. So, as you can see from the animation here, what it does is it looks at the data items and it splits them into lengths of 1, and then it merges them back in order by comparing them. So, from here, as you can see, the latest item in the list is compared, so 2, 4, 7, 8. And then what we do is we look at the leftmost item, and it compares them, so, and then it puts that into a new list. So 1, 2, and then 3 is going to go, 3 is less than 4, so that's going to go, 4 is less than 5, so that's going to go, 5 is less than 7, that's going to go, until the list is sorted. So it continually compares the leftmost items, adding the smallest to the list each time. So that is how algorithms work. Merge sort. So this merge sort algorithm here, what we have is, again, I've put it into a subroutine. So as you can see, we split and split and split using a nested subroutine until we have got one item. So if the length of the data set is greater than 1, it's going to do that. So it keeps going and going and going and going. And then it keeps splitting, and then we merge them back together. So obviously we've got this idea of merging together. So if I get this to the top, so we've got 2's list, so we've got square numbers, and then they're sorted. So thanks for watching the video. That is sorting algorithms, searching algorithms, and I hope to see you in my next video, where we'll be moving on to the second unit, looking at programming.